So welcome everybody to one of our seminars here in CFT, and today we have the pleasure of having Mohammady, and he is working now in the Institute of Physics of the Slovak Academy of Sciences in Bratislava. And today he is going to talk about quantum measurements constrained by the third law of thermodynamics. This is literally a very cool topic. So, Hamed, thank you very much for accepting our invitation. And the screen is yours.
Thank you for inviting me. And let's begin. So this is work done in collaboration with Takayuki Miyadera, who was at the time, we worked on this paper at Kyoto University. And as the title says, so the title of this talk, the subject of this talk is about quantum measurements and how they may be constrained by the third law of thermodynamics. And this falls within a larger research project, one could say, about how quantum measurements are affected or restricted by laws of physics. So I think a previous work I did, also with Takayuki and another co-author, which I presented in the seminar series, was on the Wigner-Araki-Yanase theorem, so which is how conservation laws, such as conservation of energy, restricts quantum measurements. And you could think of that as how the first law of thermodynamics constrains quantum measurements. So this is how another law of physics or law of thermodynamics restricts the measurements that can be performed. Okay. So as an outline, first I will give a very brief formulation of the third law for quantum channels, which is how the rest of the results will be formulated in terms of. Then I will give a very brief overview of quantum measurement theory, and finally I will combine the two strands into how measurements are constrained by the third law. Okay, so what is the third law? The third law, or Nernst's unattainability principle, simply says that it is impossible to cool a system down to absolute zero temperature. Now, for the remainder of this talk, I will always be considering a quantum system with a finite dimensional Hilbert space. So in such a case, when a system is in thermal equilibrium with the thermal bath at temperature T, then it is described by a Gibbs state, where H is the Hamiltonian, T is the temperature. Here, Boltzmann's constant is assumed to be 1. And so that's the Gibbs state, right? And whenever the temperature is strictly positive, the Gibbs state has full rank, as in all of the eigenvalues are strictly positive. And when the temperature is absolute zero, then the Gibbs state will have low rank, meaning that it does not have full rank. And indeed, if the Hamiltonian has a fully non-degenerate spectrum, then the Gibbs state will, in fact, be a pure state. So it'll have rank 1. So we can say that if a channel can map a Gibbs state with strictly positive temperature to a Gibbs state of strictly zero temperature, then such a channel violates the third law. Right? So taking this as a basic empirical fact of nature, how can we extract from this a meaningful universal definition of the third law for channels in general? So we may propose the following two definitions. The first definition, we say a channel, phi. So a channel is a completely positive trace preserving map. Mapping from the algebra of operators on a Hilbert space H to those of a Hilbert space K is constrained by the third law if for all states rho on the input space H, the following relation holds. So the rank of the output state divided by the dimension of the output space is larger than the rank of the input states divided by the dimension of the input space. So in the simple case where the input and output spaces are the same, this would just be a rank non-decreasing channel. Right? So unitary channels are a paradigmatic example of a rank non-decreasing channel. But when the input and output spaces are not the same, then this definition also encompasses the partial trace channel, where you just remove one subsystem of a larger composite system, or the composition channel, where you bring a system of interest together with an ancillary system initially prepared in a full rank state, right? So, of course, these are elementary procedures for general processes such as quantum measurements, as we will see later on. Now, of course, we could also provide another definition, which is in fact what we proposed in the published paper, which is that a channel, again, mapping from H to K is constrained by the third law if for all full rank states rho on the input space, the output state phi rho has full rank in K, right? Now, it is clear to see that definition 1 is stronger than definition 2, which is to say that if a channel satisfies definition 1, then it automatically satisfies definition 2. But the converse implication does not hold in general. But for the remainder of this talk, to avoid some conceptual, well, not conceptual, but technical difficulties, I will basically be restricting myself to definition 1, which is, I think, more in line with what is already present in the literature in relation to the third law. Okay. So now, of course, this definition also allows us to revisit how the third law prevents or restricts state preparations in a rather mathematically elegant way, I would say. So a state preparation on a Hilbert space H can be represented by channels as well, where the channel maps from a trivial input space, which is the one-dimensional Hilbert space, if you like, to the output space of which is the system of interest, right? And why is this the case? Why do we want to represent state preparations in this way? Well, when we say a state preparation, we're basically saying, so what is a state? Operationally, it is basically a procedure of how you can turn knobs and levers in an experimental scenario such that no matter what the input state the nature provides you, the output state of that procedure is a well-defined state which uniquely determines all subsequent measurement statistics you could possibly have, right? And this is mathematically encapsulated by the triviality of the input space, rather, right? Because if a channel maps from a trivial input space to the space of interest, then we are basically saying that the initial state of our experiment is essentially discarded. That's the rough intuition, I would say, for such a characterization. Now, of course, since the input space is trivial, is one-dimensional, then the only state on such a space has full rank on the input space, right? So therefore, using our definition of the third law, all possible state preparations will have full rank, right? Because remember, a channel is rank non-decreasing, which implies it takes all full rank states to full rank states. And since the input space is one-dimensional, then the input states, which is rank 1, but full rank in a one-dimensional space, is mapped to a full rank state on the output space, right? So therefore, this is a way of encapsulating the empirical law of nature, I would say, that you cannot prepare systems with low rank with finite resources. That's the caveat. Finite resources of time, energy, or control complexity. Okay. Now, so quantum measurements. Oh, by the way, if you have any questions, feel free to interrupt. Okay. So quantum measurements can be described in 3 levels of abstraction: observables, instruments, and measurement schemes. So I will briefly describe what is needed for the rest of this talk here. So an observable acting on a Hilbert space of interest HS, where S is the system to be measured, is represented by a positive operator valued measure, POVM, which we always assume to be discrete, right? So it's a collection of positive operators where X, small x represents the measurement outcomes and big X is the space of measurement outcomes, or the value space. And such that when you sum these positive operators, you get the identity, right? Now, these positive operators are called effects, and they correspond to properties or propositions about the system. And together with the state rho, they give rise to the probability distribution by the point, which I'm sure all of you are already familiar with. Now, of course, the standard description of observables are given by projection valued measures, which is a subset of POVMs. And these are called sharp. And so an effect is called sharp if it is a projection, and it is called unsharp otherwise. And similarly, an observable is called sharp if all of its effects are projections, and it is unsharp if at least one of the effects is not a projection. Now, we also introduced the concept of a completely unsharp effect, which is an effect whose spectrum does not contain 1 or 0, right? Because if it is possible for an unsharp effect to still have 0 or 1 as an eigenvalue, even though it is not a projection. But a completely unsharp effect has the property that it is indefinite, which is to say that the property corresponding to that effect cannot be said to exist or to not exist in any state with probabilistic certainty. Because if the effect does not have eigenvalue 1 or 0, then when you take the trace of that effect with any state rho, you get a probability which is strictly larger than 0 and strictly smaller than 1. Okay. Now, of course, while POVMs are sufficient to characterize the statistics of any measurements you would like to perform, they do not tell you how a system is transformed upon measurement. And for this, we need to use the concept of instruments. And an instrument acting in a Hilbert space, HS, is a collection of operations, which is a completely positive trace non-increasing linear map, IX, where again, X are the measurement outcomes, such that the pointwise sum of those operations, which I represent by I subscript capital X, is trace preserving. So basically, when you ignore the measurement outcomes, or when you have a non-selective measurement, if you like, the instrument gives you a channel, a trace preserving completely positive map. Now, any instrument is compatible with or identified with a unique POVM via the following relation. Right? As in, when you take the trace of the output states acted on by the operation IX equals the Born rule probabilities of a particular POVM. However, the converse implication relation is not the same, which is to say every POVM admits infinitely many E-compatible instruments. And this is an important point to keep in mind when we get to the third law. Now, the final level of abstraction for measurements is given by measurement schemes, which is an attempt to give a physical characterization of the measurement process as an interaction between the system to be measured and a measuring apparatus. So here, schematically, we have the system being measured on the first line, top line here, and the measuring device or the apparatus or the probe of the apparatus, if you like, on the second line. And so initially, the system is prepared in some arbitrary state rho, but the apparatus is given in a fixed state Z. They undergo an interaction by a channel E. And if the apparatus is measured by a pointer observable Z, which is a POVM, then upon registering outcome X, the measured system will be transformed by an operation IX of some instrument. So therefore, the tuple, which is given by the collection of the Hilbert space for the apparatus HA, the initial state Z on the apparatus, the interaction channel E acting between the system and the apparatus, and the pointer observable Z, is a measurement scheme or a measurement process for an E-compatible instrument I with the operations written as such. And as shown by Ozawa in 1984, every E-compatible instrument admits infinitely many normal measurement schemes, where the state of the apparatus is chosen to be a pure state, the interaction between system and apparatus is chosen to be unitary, and the pointer observable is chosen to be sharp. But of course, none of these need to be the case for a measurement process, which is precisely the content of this talk as we move forward. So what is a measurement scheme constrained by the third law? Well, it is as you will expect. So we just basically take the elements of a measurement scheme. We remember, well, the third law, as you recall, only pertains to states and channels, which, again, both of which can be encapsulated as restrictions on channels. So therefore, we do not impose any constraints on the Hilbert space of the apparatus, nor on the pointer observable Z. But the initial state preparation on the apparatus is chosen to be a full rank state on the apparatus, and the interaction channel between system and apparatus is chosen to be rank non-decreasing, right? And this is the only restrictions we impose. Now, of course, one could already see that the third law does not impose any limitations on the measurability of observables, which is to say that we can measure any POVM we like with a measurement scheme that satisfies the constraints by the third law. And this is shown by as follows. We just choose the apparatus to be identical to the system of interest, and then choose the interaction channel to be a swap, which is a unitary channel, which is rank non-decreasing. And since we do not have any restrictions on what pointer observable we can choose, then the measured observable E will just be the same as the pointer observable Z, right? So if we don't care about how the system transforms upon measurement, we can measure any POVM we like. But such a measurement scheme I just described to you with a unitary swap gives you a trivial instrument, which is to say that no matter what input states you have on the system and what outcome of the observable you register, the output state will always be the input state of the measuring device, right? So any information the system had prior to measurement will be destroyed. So this is a very bad type of measurement. So therefore, while any POVM can be measured by a scheme which satisfies the third law constraints, may not necessarily satisfy, so while every POVM can be measured, not every instrument can be realized by a measurement scheme constrained by the third law. And this was already shown in the case of standard von Neumann measurements by Guryanova et al. Back in 2019, where they showed that when your standard textbook measurements where you collapse a state rho onto eigenstates psi x of some self-adjoint operator, these will be forbidden by the third law, right? So now in the rest of this talk, I will basically provide some extensions of this result for general POVMs. Okay. So as most of you are probably aware, the EPR criterion of physical reality is as follows, right? It says, if without in any way disturbing the system, we can predict with certainty, i.e. probability 1, the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity, right? So if we expand this EPR criterion, we can see that it implicitly rests on the notion of an ideal measurement, which is such that when the statistics of a measurement are already known with certainty, as in one outcome is given with probability 1, the state of the system does not change. And this is the definition of an ideal measurement, which more mathematically can be written as such. So an instrument I is an ideal measurement of a POVM E if for all outcomes X, there exists a states rho such that the probability of observing that outcome equals to 1. And if for every outcome X and every state rho, the following implication holds. If the probability of registering outcome X in the state rho equals 1, then the operation corresponding to that outcome will not change the state of the system. Now, without any constraints, as in only what is required by quantum mechanics on its own, a POVM admits an ideal measurement if and only if all of its eigenvalues, or all of its effects have eigenvalue 1, right? Which should be clear to see, as in if the antecedent criterion, which is this trace EX rho equal 1, that can only be satisfied if EX has eigenvalue 1. And rho is one of the eigenvalue 1 eigenstates, if you like. But this is our first result, that under the third law constraint, as in if an instrument is implemented by a measurement scheme which satisfies the third law, then no observable admits an ideal measurement. And the reason is quite simple, once you look into it, which is that if a state rho and a POVM element or effect EX satisfies, trace EX rho equal 1, then the rank of the output state will be larger, strictly larger, than the rank of the input state, which clearly forbids the equality of these two states, right? But what about approximately ideal measurements? Now, for every POVM admits a ludus instrument, which is where the operations are such that you sandwich the input states by the square roots of the corresponding effects, right? And ludus instruments are approximately ideal, which is for any epsilon between 0 and 1, if the probability of registering outcome x in the state rho is larger than 1 minus epsilon, then the trace distance between the input states and the normalized output state will be smaller than the square root of epsilon, right? So if epsilon is 0, meaning that the probability equals 1, then the state will not change, right? So the ludus instrument of a eigenvalue 1 effect will be actually ideal. But if you have an effect which does not have eigenvalue 1, such that epsilon will be strictly smaller than 1 for all states, then you could still have this approximate ideality condition, right? And as we show, under the third law constraint, a POVM admits a ludus instrument if and only if all of its effects are completely unsharp, which, if you recall, means that none of the effects do not have eigenvalue 1 or eigenvalue 0. So therefore, if we give up the requirement that states be that effects be definite in some states, and actually accept that effects will be indefinite in all states, then the third law of thermodynamics can be made compatible with a weak or unsharp or approximate variant of the EPR criterion. And this paper by Paul Busch and Greg Jaeger proposes a program of Unsharp Reality, where they say, for many reasons, what we should give up the strict EPR criterion of physical reality pertaining to sharp effects and take unsharp observables given by POVMs more seriously. And this result gives some thermodynamic support for this research program, I would say. Okay. Now, another kind of measurement which we are usually introduced to in our undergraduate studies and textbook expositions are repeatable measurements. And as described by von Neumann, the repeatability condition is as such. So if the physical quantity R is measured twice in prompt succession in a system S, then we get the same value each time, right? So this was taken as a requirement of measurement back in the founding days of quantum mechanics. But of course, in the more modern view, repeatability is only a very special property that measurements may or may not enjoy. And well, some POVMs do not even admit repeatable measurements. And also, I should note that repeatability and ideality are not the same concepts. They coincide only when the observable is sharp and rank 1. So, your standard measurements, your standard observables represented by self-adjoint operators with a non-degenerate spectrum, right? Where where the effects are rank 1 projections. But in general, a measurement can be repeatable but not ideal, or ideal and not repeatable. Okay, so more mathematically, we say a measurement is repeatable if the following condition holds, right? So first you measure a POVM E by an E-compatible instrument I, you get outcome X, and then the subsequent measurement of the same POVM will give you basically outcome X, and yeah, with certainty. Because for any sequence X, Y, where X is not the same as Y, that sequence of events happens with probability 0. Right? Now, without any constraints, a pure VM admits a repeatable measurement if and only if all of its effects have eigenvalue 1. So this is very similar to ideality, if you remember, even though they are not the same property, which can be quite confusing. But anyway, so under the third law constraint, we can show that, again, no observable admits a repeatable measurement. And the reason for this is that for every sequence of outcomes xy, given a full rank input state rho, that sequence occurs with probability strictly larger than 0, which is in clear contradistinction to the criterion of repeatability. So therefore, repeatability is ruled out. But just as we could salvage a Unsharp version of ideality, we can also salvage a weakened notion of repeatability for general POVMs. And this is given by measurements of the first kind. Now, if you remember, a measurement was repeatable if consecutive measurements are guaranteed to give you the same outcome. Now, a measurement is of the first kind if consecutive measurements are guaranteed to give the same statistics, right? Which mathematically you write as follows. So remember, I capital X is a channel, a trace preserving map, which gives you what happens to the states of a system upon a non-selective measurement. So here we're saying that we perform a non-selective measurement, so we don't keep track of the measurement outcomes, and then we make a measurement of the same observable again, and the probability of that second measurement is the same as had we not made the first measurement, right? And well, if you go and play around with the equations, it should be quite clear to see that repeatability implies first kindness. As in, if you take the repeatability condition from the previous slide, if I go back here, so if you take this equation and sum over X here, essentially, then if a measurement is repeatable, then it will also be of the first kind. But the converse implication only holds if the observable measured is sharp, as in if all the effects EX are mutually orthogonal projections. But in general, a measurement can be of the first kind, but not repeatable. So therefore, the no-go theorem for repeatability does not preclude the possibility of first kindness. And as we show, under the third law constraint, a pure VM admits a measurement of the first kind only if all of its effects are sharp. So, all of its if its effects are completely unsharp, I should say. Sorry. So complete unsharpness is a necessary condition for first kindness given the third law. And if we add to complete unsharpness also commutativity, meaning that all the effects EX mutually commute, then we also have sufficiency for first kindness. And this is because a Lüders instrument of a commutative observable is a measurement of the first kind. And as we showed in the previous slide, a POVM admits the measurement of the first kind. Sorry, a POVM admits a Lüders instrument if its effects are completely unsharp. Okay, sorry, it's a bit of a mouthful. Right. So, yeah, I think that's basically it. I'll just conclude, and I think we should have plenty of time for questions after this. So first, we provided a general formulation of the third law for channels with arbitrary input and output spaces, which is a generalization, I would say, of rank non-decreasing channels. And then we proposed in measurement schemes constrained by the third law, where the probe or the measuring apparatus was prepared always in the state of full rank, and where the interaction between system and apparatus is rank non-decreasing. And then we showed that measurements which are constrained by the third law cannot be ideal or repeatable, but we showed that the third law does allow for weakened forms of ideality and repeatability. And this was done if only if rather the observable measured is completely unsharp, such that the events associated to the every outcome of said observable would be indefinite in all states. And yeah, that's it. Thank you for your attention.
Thank you very much, Hamid. Now we have plenty of time for questions.
So I have a question. Sorry to ask actually elementary question, but you start with the third law of thermodynamics. You cannot reach the zero temperature. That's the difference from actually the
Yes.
statement. I remember, but actually maybe it is equivalent. Can you explain why? I mean, this is about actually entropy, constant entropy at actually T equal 0, but these states, you cannot reach the zero temperature. I mean, is the same equivalent or?
So sorry, could you repeat your question? So
Like
what do you,
I
what
remember
is equivalent?
I remember the third law of thermodynamics. Actually, when you go to the zero temperature, the entropy become constant, right?
Right. Yes. Okay.
But this is the same. You said the system cannot cool down the absolute zero temperature. This is equivalent to the.
Okay. I'm not sure if the two statements are equivalent. So I guess people say different things about the third law, but I think the non-reachability of like absolute zero temperature, I'm guessing it is the same, but I can't be absolutely. I can guarantee that. But this is what I've read in the literature myself. I'm not an expert on the third law myself. That should be a caveat. So I'm just taking the third law as a empirical law of nature, that it just so happens that we cannot cool systems to absolute zero, right? And I think, and there are arguments why this is not achievable with finite energy or finite time, right? So if you want, so roughly speaking, how do you cool a system down to zero temperature? Well, you say you couple it to a thermal bath of infinitely large, like an infinitely large thermal bath, right? But if the bath is infinitely large and you want to use that, and if you want to make your system of interest interact with such an infinitely large bath, that roughly speaking implicitly assumes that you have infinite time, given a realistic like interaction which happens just locally, right? So if you only have finite time, or if you can only interact with a finite subspace of your thermal bath by a unitary interaction, then it's kind of a trivial bit of mathematics to show that you cannot reduce the rank of your system of interest. But that kind of an argumentation is kind of tautologous, I would say. So I think it's just more honest to say it's just an empirical law of nature I'm taking as a given. And then I will see what consequences can be derived from this if we take it as an empirical law.
So
Sorry, did that answer your question? Maybe not.
Also, along this answer, you assuming the some thermal reservoir, right? It's not, you are not just talking about one particle, like two particle system. You are already consider some big reservoir, right? And the system is thermally equilibrium with the reservoir, right? And then you can talk about a third law. Otherwise, you have single particle. You cannot actually. You already said that temperature is zero, right?
Okay. Yes. When you're talking about temperature, then yeah, you're talking about ensembles and Gibbs state. Yes. If you don't have a Gibbs state, then yeah, the concept of temperature becomes more
meaningless.
Well, it becomes more nuanced, I would say. But okay, a single particle, you can still assign a temperature to a single particle. I mean, this is how Szilard envisaged his engine, right? Where you have a single particle gas, but you have an ensemble of such things. So, and in a quantum mechanical experiment, you still have repeated measurements or you don't have a single run of an experiment. You have many runs of an experiment on a single particle. So then taking that as an ensemble, you could still assign that a temperature in the same way as Szilard did, I would say. But anyway, so I'm not really taking a thermal bath here implicitly. Okay, this is the philosophical approach we were taking. We assume the third law is an empirical law of nature, that in labs, in real experimental situations, we cannot cool systems down to absolute zero temperature, or taking that to another level of abstraction, that we cannot prepare systems in states of low rank, right? And then we say, okay, what is the minimal formulation of the third law which conforms with this empirical law, right? And that's how we arrived at these possible formulations of channels, right? So, of course, you can argue that maybe the third law is wrong. Okay.
Yeah, I mean,
would
I
not,
also
argue with
like
that.
to say, I mean, this the title can be like a reverse. So you can say third law is not correct. I mean, some sense because
Right. Right. Yeah. If you assume that in experiments you have perfect ideality of measurements or perfect repeatability, then, well, yes, you either have to give up the third law, or you have to give
Right.
up the quantum mechanical description of the measurement process, right? So
Right.
maybe the third law is correct, but maybe measurements
Right.
are not actually described physically
Right.
as follows, right? So you could
Right.
give up either of those two things.
Right.
So
Okay, thank you
I
very
wouldn't
much.
say the results show that the third law is wrong,
Okay.
right? It's not sufficient. But
Yes.
yeah, if you want to assume the universal validity of quantum mechanics, then yes. But if you can actually show experimentally that measurements are ideal or repeatable, then you will have proven that the third law, as formulated here, is not true. But I don't think that's something that can be proven experimentally, right? Because how can you prove that a measurement actually is repeatable? Because you would need infinitely many measurements, right?
Right.
Right. So, but yes, in principle, one could draw such a conclusion if one were so inclined.
Okay. Thank you very much.
Sure.
Hamid, I have a question. So you brought
Yes.
to us the definition of elements of reality from EPR, right?
Yeah.
I would like to know your opinion about that, because in that paper, they never say anything about mixed states.
You mean the
So-
original EPR paper?
Yes.
Right. Sure. Okay.
They never say anything about, and then that is a problem, because if you have a mixed state, then you have classical uncertainty about that, so you cannot predict with certainty the result of the measurement. But would you say that a maximally mixed state, for instance, would have elements of physical reality associated?
Okay. Well, I mean, there's just a technical. Just because you have a mixed state doesn't mean that it does not arise to a outcome with probability 1, right? Because if you have a two-dimensional projection, you could still have a two-dimensional state, as long as that state lives in the support of that two-dimensional projection, you still get probability 1, right? So I would say that purity is not necessary for the APR criterion to hold. But your second question, a mixed state, does that correspond? Sorry, a maximally mixed state, would that correspond to an element of reality? Well, okay, but if you have, again, just classical mixture, right? So it's just a ignorance uncertainty, then a mixture is still not an element of reality, right? Because you're already assuming the actual elements of reality are the eigenvalues, and now you just have a probability distribution over them. The probability distribution is not itself an element of reality, I would say. So, yeah, I would say, yeah. So I'm not sure if that answers your question, though.
Yes, partially. Thank
Okay.
you. Do we have more questions? Okay, so I think not. Okay, so we can finish for today. Hamed, thank you very much for giving this talk. If anybody else has some questions to do, they can send you an email. Once again, thank you for accepting our invitations, and see you guys next time.